Now let's do some examples. Here we are going to prove that the function ex will have a Maclaurin series, right? Like we are going to prove the existence of a Maclaurin series for this function. So when you are proving the existence, it is not correct to evaluate a power series through these computations, right? Now you cannot do this one when it says to prove the existence of a power series, because you can do this for all infinitely differentiable functions. But we saw in a certain example, remember that e to the power negative 1 over x squared 0 function, we were able to calculate all these terms, but still it did not, like, it gave a contradiction when we write down the power series to be equal to this given function. So my point is, when it says to prove the existence of a certain power series, it is not correct to evaluate these coefficients and write down the sigma notation, right? This is a way to find the power series when you know that such a term, or I mean such a series exists. So before going into this one, we should make sure that a power series will exist for this function, right? So for that, we learn only thing which is required is to prove this inequality, because when you have this inequality, you have this one. When you have this one, that means you have this one. So when you have this one, it says that a power series exists. So what we are trying to do is to prove that this inequality exists. Now for this one, m can be any non-negative integer, right? So what we need to do is we just have to prove that the n plus 1th derivative is less than or equal to m, right? Then our function is fx is equal to ex. So if we calculate the derivative of this function, it will be the same, right? So that means the fn plus 1th derivative is also equals to e to the power x. I took fn plus 1th derivative because in the result we need the fn plus 1th derivative, right? And then we need this condition. We need this derivative to be less than or equal to some number for a given integer, I mean for a given range of x. Now here, as we are going to prove the existence of a Maclaurin series, our center value will be equal to 0. So basically what we need to do is this one. For a given range of x, we have this inequality. Then we can say that for this range of x, this inequality is satisfied. So for that particular range, the remainder will go to 0, and when remainder goes to 0, for this particular value, a Taylor series will exist. Now just suppose d is any positive number, right? So for any positive number, when x is less than, let's have the non-strict inequality, less than or equal to d, we can easily say that our function, the n plus 1th derivative, which is equal to e to the power x, and this is a increasing function, right? So we choose x from this interval, right? And the highest value that this function can take within this interval will be the function value that corresponds with this d. So definitely it will be greater than or equal to e to the power d, right? So we can consider this as our integer m. Now see, here in this result, what we have is a certain number where the n plus 1th derivative is less than or equal to that certain number, right? And this inequality should be true for this given interval. So basically, this number and the interval will depend on each other, right? And therefore, what we can do is, when we have, if we consider m as e to the power d, so eventually what we have is, for all x values in x less than or equal to d, we have fn plus 1, the n plus 1th derivative less than or equal to m, which is equal to e to the power d in our specific function. So we have the required condition for that second result. So from this condition, we can say the conclusion of our second condition, which is this one. And that means for this particular range of x, so that particular range of x, for x less than or equal to d, this relationship is true. That means Rn, the modulus of Rn will be less than or equal to m n plus 1 x n plus 1, right? Now here in this case, m is actually equal to e to the power d, right? So when you have this condition and limit, what we have to do is, we just have to get the limit of Rn, and for that we can make use of this standard resulting limits, which is equal to 0. So when you take the limit in both sides, since you have this format in here and this is a constant, this limit will go to 0. Therefore, since this is also greater than or equal to 0, from the squeeze theorem, we can safely say that the limit of Rn will go to 0 for our chosen x values. And since you can do this for any d, that means now if you choosing a d means we restrict the values of x that we are considering. But since we can expand this range, this result will be true for any value of d that we consider. So in other words, this result is true for any x value. That means for all the real numbers, this result will be true. Therefore, eventually, what we can say is, for any real number, you will have the remainder going to 0. And remainder going to 0 means you will have a power series, or a Taylor series. And in this case, it's actually a Maclaurin series for the given function fx.